In this video, you will learn about the quotient property of exponents. First, let's explore what it looks like when we divide exponents with the same base. Now, if I were to look at what I have here, and I rewrote this as 5 to the 6th, this could become 5 times 5 times 5 times 5 times 5 times 5. So I have it 6 times. And then my denominator is 5 to the 2nd. So I have 5 times 5. So there's two 5s. Now if I simplify it, these 5s cancel and these 5s cancel. So you're left with 4 of these 5s. So I can rewrite it as 5 to the 4th. Now if I look at the original exponents, I have an exponent of 6 and an exponent of 2. Now, if we were to try to use the exponents to get to that same relationship of 5 to the 4th, if I think of it as 5 to the 6th over 5 to the 2nd, and if I think of this as subtracting the exponents, so it becomes 5 to the 6th minus the exponent of 2, I get the result of 5 to the 4th power, as shown here. Now this leads us to the following property of exponents, which says when dividing two powers with the same base, you subtract the exponents. And we have to note that no bases can be equal to 0. So if I were to write this formally, the quotient property of exponents allows us, when we have two exponents with the same base and they're being divided, it allows us to subtract the exponents. So we subtract the top exponent minus the bottom. So I can rewrite this as a to the m minus n and simplify. So if I were to follow this practice in this example below, they both have an exponent of x. My top exponent is 4 and the bottom is 2. So if I rewrite this, it becomes x to the 4 minus 2, which I can further simplify to get your answer of x squared. And this shortcut works whenever we are dividing exponents. So in our first example, we notice that both of the numerator and denominator have a base of a, so this allows me to subtract the exponents. So I have my exponent of 6 and the exponent of 14. So I can rewrite this as a to the 6 minus 14. Now when I simplify, 6 minus 14 gives me a value of a to the negative 8th. The last thing I have to deal with is, because of the fact that I have a negative exponent with the negative 8, this means I have to rewrite this as a fraction and bring this whole expression to the denominator. So I have a to the 8th on the bottom with a 1 left on the top. So your answer is 1 over a to the 8th. In this example, both the terms have a z as the base, so I can subtract the exponents. So I can say it's going to be 10 and the 5 will be subtracted. So if I rewrite this, it becomes z to the 10 minus 5. Then when I simplify, 10 minus 5 gives us 5. Since it's a positive exponent, there's nothing else we have to do, so z to the 5th is our final answer. In this example, I again see that both terms have a b as the base, so I can subtract the exponents. So I have a 4 in the numerator as the exponent and a 9 in the denominator. So I can rewrite this as b to the 4 minus 9. And when I simplify, 4 minus 9 gives us a negative 5. Now we do notice that this is a negative exponent, which means that I have to take this whole term and bring it to the denominator. So I have b to the 5th in the bottom, and I'm left with a 1 on the top. So your answer is 1 over b to the 5th. Now in the next example, I have to deal with multiple variables. We can see that I first have a c term in the numerator and denominator, and my exponents are negative 1 and 5. So I'm going to rewrite this with the c terms, and I start with the numerator exponent of negative 1 minus the denominator's exponent of 5. Then I'm going to address the d's. So I have two terms with a d. One has a 3 and one has a negative 4 as an exponent. So I can rewrite this as d, and my exponents, I'm going to first include the numerator's exponent of 3 minus the denominator's exponent of negative 4. Now when I simplify, the 1 minus 5 gives us a value of c to the negative 6. And if I simplify the 3 minus negative 4, we know this is really the same thing as saying 3 plus 4. So this becomes d to the 7th. Now the last thing I have to do is look for negative exponents. And I can see that I have a negative exponent on the c. So I have to take this whole term of c to the 6th and bring it to the denominator. So I have c to the 6th in the denominator, and I'm left with a d to the 7th in the numerator as my final answer. In the next term, I'm going to start by grouping by the base of the exponents. So both of these terms, there's an a in the numerator and denominator. Their exponents are 2 and 4. So if I go to rewrite this, I'm going to have a, my numerator's exponent is 2, minus the denominator's exponent of 4. Then I have a b in the numerator and denominator. The term in the numerator doesn't have an exponent, so I assume it's a 1. And the denominator has an exponent of 3. So now if I'm to rewrite this, it becomes b, my numerator's exponent is 1, and my denominator's exponent is 3. So it's 1 minus 3. Now if I simplify, a to the 2 minus 4 becomes a to the negative 2, and b to the 1 minus 3 becomes b to the negative 2nd. And lastly, I have to rearrange by addressing the negative exponents. As you see, I have a negative exponent with the a and with the b. So this means that this is over 1. I'm going to take the whole a to the 2nd term, bring it to the denominator, and the whole b to the 2nd term and bring it to the denominator. It becomes a to the 2nd, b to the 2nd, and there's nothing left in the numerator, so I just have 1. So your answer is 1 over a to the 2nd, b to the 2nd. Now I have 3 variables, but I'm going to just follow the same process with all 3 variables. So my first, I have an x in the numerator and denominator. The x in the numerator has an exponent of 1. The bottom term doesn't have an exponent, but I'm going to assume it's a 1. So I can rewrite this as x, and it's the numerator of 2 minus the denominator of 1. Then I have a y in the numerator and denominator. My y in the numerator is negative 1, and the exponent in the denominator is 4. So I can rewrite this as y, the numerator's exponent, which is negative 1, minus the denominator's exponent of 4. And then lastly, I have a z in the numerator and denominator with the exponents of 4 and negative 3. So this becomes z the exponent in the numerator is 4 minus exponent in the denominator is negative 3. So it's minus negative 3. Now when I simplify, x to the 2 minus 1 becomes just x to the first power. Then the negative 1 minus 4 is going to become y to the negative fifth. And then lastly, we know for the z, if I'm going to combine the 4 minus negative 3, the minus and negative is really a plus. So it becomes 4 plus 3. So this means I have z to the 7th. Now the last thing I have to do is simplify. The first thing is I see I have an x to the first power, which we know when I have a first power, I actually don't include it at all. So that's going to go away. So it's just an x term. Then I have a negative exponent of 5. So this means I'm going to take that whole term of y to the negative fifth and bring it to the denominator. So I have y to the fifth in the denominator, and I'm left with x z to the 7th in the numerator. Now, if I look at something like I have here, where I have x over y raised to the third power, what this really means is I'm multiplying x over y times x over y times x over y. Now I can rewrite this as x times x times x over y times y times y. And this simplifies to become x to the third, y to the third. Now, rather than writing this out in all these separate steps, essentially what I really could have done is thought of this as multiplying the third power to the y and the x. So it becomes x to the third, y to the third. And this gives us another property of exponents we can use. When you're raising a fraction to a power, raise the numerator and denominator to that power. So what we can see with the example here is if I had 4 over 5 raised to the third power, you're multiplying the 3, or raising the 4 to the third power and the 5 to the third power, like we see here, and then it simplifies. So when I apply that property, I multiply the exponent of 2 to the third, the 3, and to the x squared. Now when I do this, my term of 3, I can rewrite this as it becomes 3, and it's raised to the power of 2. So I get 3 to the second power, and the denominator's term of x squared becomes I have x squared, and that is now raised to the second power. Now for the numerator, when I simplify that, it becomes 3 times 3. And in the denominator, this means I'm going to multiply these two exponents using the power rule. So it becomes x to the 2 times 2. And when I finish simplifying, 3 times 3 is 9 over 2 times 2 is 4. So your final answer is 9 over x to the 4th. Now if I follow the same process for the next example, I'm raising both these terms to the third power. So I multiply the 3 to the x and the 3 to the y squared. So if I take my numerator of x, so I can rewrite this as x, and it's now being raised to the third power. And my denominator of y squared is now being raised to the third power as well. So it becomes y squared raised to the third power. Now the numerator I can't do anything with, so it just stays as x squared. And we know in the denominator, I'm now going to multiply these exponents using the power rule. So it's over y to the 2 times 3, and when I finish simplifying, I get x squared over y to the 6th power as your final answer. In our last two examples, we're going to deal with our negative exponents, and we're going to follow the same process to start. So for the example on the right, I'm going to take the negative 2 as my exponent and distribute it to both the numerator and denominator. So if it distributes to the 3 as my numerator, I can rewrite this as being 3 raised to the negative 2nd power. And it's also distributed to our denominator of 5. So it becomes 5 raised to the negative 2nd power. Now the last thing we have to do is, before I can think about simplifying, I need to rearrange my terms. So we see that the numerator has a term of negative 2. So I'm going to bring this whole expression to the denominator. So it becomes 1 over 3 squared. In the denominator, I also have a exponent of negative 2. So I'm going to bring this whole expression to the numerator. So it becomes 5 squared. Now when I simplify this, I have 5 times 5 over 3 times 3. So it becomes 25 over 9. Now had we wanted to flip this originally, because I had this negative 2 as an exponent, I could have rewrite it as 5 over 3 and gone through this process, but it involves us to identify that negative a little bit sooner. And in the last example, we're now going through the same process with exponents, where I will distribute the exponent of negative 3 to the numerator and the denominator. So when I rewrite it, the numerator of 7a, I get 7a, and the whole thing is raised to the negative 3rd power. And the denominator of m is now raised to the negative 3rd power. Now when I simplify, in the numerator we know that 7a to the negative 3rd is really distributed to the a and the 7. So it becomes 7 to the negative 3rd, a to the negative 3rd. And the denominator can't be simplified, so it's m to the negative 3rd. Now what we should notice is that the numerator, these both have exponents of negative 3. So it means I'm going to take the whole thing and bring it to the denominator. So I have 1, so it's over 7 to the 3rd, a to the 3rd. And in the denominator, I have an m to the negative 3. So I'm going to bring this whole term up to the numerator. So it's m to the 3rd power. Now the only thing I have to further simplify is we see that we have this value of 7 to the 3rd, which I need to rewrite in terms of a whole number. So if I rewrite this, it's m to the 3rd over 7 times 7 times 7, a to the 3rd. And when I finish simplifying, if I do 7 to the 3rd power, it gives me value 343. So your answer is m to the 3rd over 343 a to the 3rd. And again, like we had in the previous example, you could have flipped the fraction initially and simplified from there.